And there's one more explanation for it, at least if I know if the one to the right is, if this one is to the right, how do I know that one has to be to the left?
North and south poles.
Not a north-south pole thing. I think physics 251.
Just that all forces have equal opposites.
Newton's third law. If they were in the same direction, then in theory you could have two wires, set a current running in opposite directions, and then they would somehow propel them this way. The net force of the universe is 0. I've suddenly realized I'm ignoring a bunch of stuff, but let's simplify it down. All right, so in the experiment that you did, I had current running down one side and up the other side, and that's why it puffed outwards. If I had two strips of aluminum foil with two different power supplies, so the currents were going in the same direction, they would get sucked together. I do throw in one caveat here. If the room is haunted, then strange things can happen. I did have a group that had set this up. We were in the other building, which I assume is above the Indian burial ground. And they turned the power on, and the two leaves would go, and so they called me back. It was the back right part of that room was always getting weird things, but that was one of those bizarre. So I went over there and I looked at it, and indeed, you turn on the power, and the two sides of that aluminum foil go. And so what I did was I switched the leads into the power supply. So instead of the current going this way, it went that way, and they puffed out. No idea why. I guess the ghosts were scared or something. It was just bizarre. And I had one of my former students from here doing engineering at NC State. I posted it to him, and he said, "Oh no, let me go ask my professors at NC State." And it basically came back and was not quite sure about why it happened. I have a germ of an idea dealing with, there was an extra fold in the paper in the aluminum, but it just still seems odd. All right, so other than haunted experiments, they're forced outwards. So if these are a distance d apart, then I know my red magnetic field here. So the magnetic field at, let's see, that's 1, that's 2. So the magnetic field at 2, because of 1, is going to be mu naught times current 1 over 2 pi yeah, 2 pi d. And our notation right here, it would be in the hat, right? I know that the force on wire 2, the force on 2 because of 1, is going to be equal to the current 2 times the length of that wire across B. So this distance here is L. My L vector is in the direction of the current, which is up. My magnetic field is out, so my current is up, my field is out, so the force will be to the right in the I-hat direction, given our notation. So this is going to be I2 times that length times my magnetic field there, which is mu naught I1 over 2 pi d. Rewriting that slightly, the force on 2 from 1 is equal to mu naught I1, I2 over 2 pi times the distance between them, times the length I had. In the lab, one of the ways, one of the ways that you're figuring the force that's acting on it is if you assume that they are wires, what is the force acting on it? And that's the one that is gonna be probably the most off. Because you'll find three different forces. One assumes that they're sheets with a current flowing through it, and I gave you that equation. That was that really long equation, and I'll be glad to share the derivation with you if you wish. I do not plan to do the derivation in class, but it's, a fun calculus problem. Maybe just when you got nothing better to do, try to drive it yourself. One of them is the force based on assuming that they're wires, this equation, and one of them is the force based upon the modulus of elasticity and how much it puffs out. I mentioned this to Benjamin, but I put your numbers into my spreadsheet and I tried to see what was the best possible outcome in terms of percent difference. And there is a combination that will get you a percent difference of 0.27%. I don't know if I made your life more complicated or easier now, but there is a combination that gets a really good percent. There's also a combination that will get you 200% difference, which you can't get worse than unless you had a negative number in there, a negative force.
So 0.27?
0.27. Yeah, not 27%, 0.27%. Questions to hear? I'm not going to derive the long equation, I just want to at least set up how I went about it. If I have a strip of aluminum foil here, and another strip of aluminum foil here, they're face to face, not side to side. I basically treated this as I have an infinite number of infinitesimally skinny pieces of aluminum foil, and treated each one of these like a wire. So it basically found the force from this wire onto all of those, and then the one next to it onto all of those, and I'm doing an integral. And I come up with that equation. What have I not talked to you about? That. That. Not done that yet, sorry. Questions before we do something related but different? Do we need stretch legs? Take a small break here? Or you're just too excited to take a break? Oh man, the enthusiasm, I'm just feeling the energy you're giving off. This is great. Especially Sarah. So just even thought. Now the international community is going to wonder, who is Sarah? What is she thinking about? Still one of those bizarre things. One of my lectures had 29 views. What? Why? Most people were in class. I don't think that one person watched it. Or I'd be surprised if that many people from the class had actually watched it.
What's the most views you've ever gotten on a video?
I have two with a couple thousand. My right-handed coordinate system right now is the most views, and then converting Cartesian coordinates, it's part of the Kepler's law series. Putting it was a polar Cartesian for an elliptical flight, converting the formula of an ellipse from Cartesian into polar form. That was it. That's the other one. There's even a demand for a sequel to it, of going the other direction. Okay, one person put in a request. So I have a current going around a rectangular bit of wire. And of course, I'm going to expose it to a magnetic field. Let's make the magnetic field be going to the right. All right. What I want to figure out is the torque acting on this wire. So the first thing we need to do is figure out forces involved, the direction of forces. And I think it look like the top and bottom are not in the magnetic field. Magnetic field is, the whole thing is bathed in this magnetic field. What is the direction of the force acting on the right side of the wire? Why don't I go ahead and label those just for purposes of identification. So we'll call this wire, this part 1, 2, 3, and 4. So in segment 1, what is the direction of the force?
Into the board.
All right, so how did you figure that out? You do a cross product or right hand rule? Or combination thereof?
Right-hander rule.
Right-hander rule? Okay, so currents cross magnetic field, okay? Or doing the Sten gun, direction of current, direction of magnetic field, force into the board. All right, so I have a force here, so F1 into the board. What about on segment 2?
Would it just be 0?
It would indeed. Why? Oh, you got that part and so it's someone else's turn to take over?
Well, I mean, I just remembered that the cross product, when there's either 180 degrees or 0 degrees between them, if they're parallel or whatever the
Anti-parallel.
antiparallel, it's 0.
Yep, that's good enough. All right, so 0 force. All right, what about segment 3?
Out of the board.
And how'd you get that?
Right-hander rule again.
Okay. Also, of course, going the opposite direction should be the opposite of what this one was. So my force 3 out of the board. And what about segment 4?
0 as well.
All right, so I have this wire here where I have one force pushing on the right side, another force pushing out on the left side. It is, of course, going to rotate. As it rotates, we have torque involved. So what is the axis of rotation?
Is it like that? Halfway between the 2, 3, and 1?
All right, so there's our axis of rotation. The distance here would be A over 2 and A over 2. So let's figure out the total torque. So the torque I know is R cross F. I have two torques, so it's going to be R1. Why don't I just make it R1 cross F1 plus R3 cross F3. And then if you're really being pedantic, plus R2 cross F2, but that's equal to 0, so there it is. R1, that is A over 2 I hat cross, what is the magnitude of F1? We identified that it's going into the board, so that's negative K hat. But what's the magnitude of force 1?
Is it the current times 1 cross, or the length cross with the magnetic field? Current
So the
times
current
L cross B,
times the length,
L1, or
so B. It's in blue, sort of hidden behind there, but B is that length.
oh,
And then the direction we've already established, so, so little b, big B. Plus R3, negative A over 2 I hat. Cross, I know it's going out of the board, and then I, little b, big B. I cross negative K. I have I cross negative K there and negative I cross K. So we'll get the same answer, which makes sense. I mean, they're both causing the thing to turn. What is I cross negative K?
Positive J.
So I cross negative K, all right. So I have A over 2 I little b big B J hat plus A over 2 I big I little b big B J hat. And we can combine. That's equal to. So again, this is the torque acting on the wire. I have half an A here, so I end up with I, B, little a, little b, J hat. What is A times B? Little a times little b.
Area.
Yeah. So this is I, B, that's the area. And so it's a little bit more universal. If I made it, if it were a circle instead of a rectangle, it would still be the area. Try to do this part right. If I take the current times the area, this is known as the magnetic moment, magnetic dipole moment. And the symbol, because we've run out of letters, is mu. It is a vector, so I guess technically. And the direction of the vector is going to be, well, if I is going around clockwise, it would be out. Sorry, I is going counterclockwise, it's the direction of that. And so mu is equal to I, A, and in this particular problem, K hat.
Is there a generic way to say like a direction vector that's not specific I, J, or K, or R?
It won't be satisfied, I don't think. There's the generic, you just stick the hat over the vector. Is that satisfying?
Yeah.
Oh, okay, then I was wrong. I did not think it would be.
I mean, that works.
So the torque was up, so I have B going off to the right, I have mu coming out of the board, and so if we do mu cross B, we end up with a torque. So I could also write the torque generically as U cross B. Now I do have a video that addresses this next bit. Well, I have a video that addresses almost all of it. But please, do not confuse the mu's. Mu sub S, U sub K, U sub R are coefficients of friction. U sub naught is the permeability of free space. U by itself is the permeability of the material, or it's the magnitude of the magnetic dipole moment. So in one context, it's just mu, in another context,